Hi everyone, and welcome to a new episode of the Allplane podcast, where we talk with the movers and shakers that are redefining the future of commercial aviation. As usual, before we get into today's episode, I would like to remind you that you can find all the previous episodes of this podcast, as well as many other aviation stories on the Allplane website. That's Allplane.tv, Allplane.tv. And I also would like to use this opportunity to invite you to subscribe to the Allplane newsletter, which focuses on sustainability and innovation in the aviation industry. So just go to the Allplane website, and there you will find the link to subscribe to the newsletter. And now to today's episode. Our guest today is Scott Drennan, an industry veteran with decades of experience at companies such as Bell Helicopters and Supernal, which is Hyundai's eVTOL arm. But Scott is today here to talk about another company, of which he is the president and chief operations officer, and that is Otto Aviation. If there was a ranking of the companies that are pursuing the most truly disruptive projects in aviation right now, Otto Aviation would come very, very near the top. In fact, one of the things I find so interesting about the present moment in aviation is the fact that companies like Otto Aviation are really trying groundbreaking solutions to make flying more efficient and more environmentally friendly. If you have seen the Otto Aviation Celera 500L bullet-shaped prototype, you will know what I'm talking about, because this is a truly unique aircraft. And while Otto Aviation has already moved past the Celera and onto the development of a clean sheet business jet called Phantom 3500, the concept remains fundamentally the same, and that is using a physics principle called laminar flow in order to achieve an unprecedented level of aerodynamic performance and fuel efficiency. With Scott, we review the main principles underlying this idea, and we also talk about how far Otto Aviation has got in the pursuit of this project and what are the company's industrial and commercial rollout plans, particularly after having received the backing of the state of Florida. Otto Aviation is in fact preparing to build a greenfield factory in Jacksonville, Florida, which is going to be its main production facility in the future. But I think it's best if we hear it all directly from Scott. So without further ado, let me welcome him to the podcast. Hi, Scott. How are you?
Doing well, Mikel. Thank you.
Thank you so much for being here today on the podcast. Just let me make a quick introduction. You are Scott Drennan, president and COO of one of the, I would say, most interesting projects in aerospace right now in the US and in the world, because it's truly original, truly eye-catching, and it has a number of technical features that I think make it very interesting and also potentially very transformative.
Yes.
Talking about Otto Aviation and the aircraft you're designing to take advantage of a phenomenon called laminar flow. We're going to go into more detail into this technology. But first of all, can you please just tell us about yourself, a couple of lines, so that just to set the context?
Yeah. Well, thank you for the introduction there, Miguel. I am Scott Drennan, as you said. I've been in aerospace and defense for about 32 years now. Most of that time was spent at Bell Helicopter over in Fort Worth, Texas. Worked on most of their tilt rotor platforms and helicopter platforms over many years of really great experience there. I finished up as their VP of Innovation, and so I was in charge of the Nexus and their eVTOL offering, the stop fold and high-speed tilt rotor that you see that's out there now finally was a part of our world and innovation as well. And then when I left Bell, went and helped Hyundai set up Supernal. I was a colleague of Jay Wan's, and we did a little bit of that together. And then I went out on my own, and that's where I discovered Otto. I was a advisor for the New Vista Capital Company, which is run by Dennis Muhlenberg, the ex-CEO and chairman of Boeing, and some of his partners. And we went to take a look at Otto, and here I am 2.5 years later, proud to be a part of it. And I think, well, like you said, we're really doing something very transformative.
Yes, I've seen that you are also an advisor at Regent, the company
I am,
design.
yeah. Yeah, the Sea Glider guys.
Yeah, another very interesting and transformative project. I've got Billy here on the podcast as well. And
Excellent.
And that's another project that I think I advise everyone to have a look at if you
Oh,
haven't,
yes.
because it's also really, really interesting. And I think they are doing great progress now with the tests. Yeah. I'd
Yeah,
see.
yeah, they're out there on the with the full size on doing sea trials. We'll hook up with them someday. Maybe we'll do the long leg, and they can do the coastal shorter legs. It'll be a great combination.
Indeed, yeah. So let's get into matter with Otto Aviation, because that's a private company. I read a little bit about the beginnings, founded in 2008 by Bill Otto. That's why the name
Bill Otto Senior, yes.
Otto
Uh-huh.
Aviation, yeah. And at the beginning, the project was a bit different. I think the aircraft, the approach was similar in the technology approach, but you had a plane called the Celera 500L
Yes.
that has been it flew already. I think in 2018 it flew for the first time. It did like 50 something test flights.
Yep.
Then at some point, I was tracking this project. At some point it kind of went mute, disappeared from the radar a little bit, and then it recently re-emerged on the public stage. I mean, I'm not saying it went away, but I
Yeah.
kind of kept a low profile for a while, and then it re-emerged with a kind of I don't know if it's how different the project is from the original one, but it got definitely not a rebranding, but a new aircraft name, the Phantom
Yes.
3500. I think the approach is a bit different. You are now focusing on the executive jet
Yep.
space. And I think you're still kind of using the same concept, but with a few differences. So I think it would be great if we just start by the very beginning,
Sure.
just start by the origins of Otto Aviation and how this project has been evolving. And then we can maybe go in more depth into what you
Sure.
are guys doing now and what makes this project so unique. Yeah.
Okay, great. Yeah, if you go back, it's a fun kind of history, actually, especially with Dr. Otto, Bill Otto Sr. We always make sure people know that Bill Otto Jr. is on our board still. Of course, Bill Otto Sr. is kind of an emeritus, participant in Otto today. But back when he was a younger man, he worked in laminar flow, but in a different field in hydrodynamics, where he was assigned by North American to help torpedoes go further and be more efficient. And we always take for granted that shape of a torpedo today because we don't think about the history of it, but there was a different shape before and it wasn't so efficient. And he and his team helped apply laminar flow, and that famous, I guess, Mark III or Mark IV torpedo became the Mark III or Mark IV Dolphin torpedo. And there went the history. Well, and then he became interested in applying laminar flow concepts to aviation. He did a few other things in between, but that's when Otto Aviation was founded. And yeah, I think it's somewhere in that 2008 to 2010 time period that it was founded. And the team was very small and scrappy. And they created I don't think your audience will get to see it, but they created the aircraft that you see behind me here today, the Celera 500, as you referenced. And the Celera 500 was a turbo diesel pusher prop that weighed about 9,000 pounds. And it was meant as a technology demonstrator for natural laminar flow.
If I
Yeah,
stop you 1 second, when you say a pusher prop, it means that the prop is at the back of the plane, yeah?
that's correct.
Just
Yeah.
making the precision here for everyone to understand. And also, as you mentioned, this is going to be on audio, so people won't be able to see it at the same time. But I'm going to post some pictures, of
Okay,
course,
good.
on and videos in the show notes. But just let's say that it's an airplane that it's been described a bit as a drop of water when it comes to
Yes.
the shape, right? I mean, you mentioned the torpedo. I mean, that's also possibly a good analogy. I'm not an expert in torpedoes by any means, but I guess
Well,
people can get to understand what we're
yeah,
talking about here.
yeah. Think of an elliptical bull or a bullet shape. A lot of people associate it with a bullet shape. It's funny you brought up Regent. You often see in high performance ships like theirs, especially high performance yachts. You'll see these bulbs at the bottom of their outriggers, and they have the same shape as our fuselage because they're looking for very, very low drag as those bulbs enter the water.
Yeah, actually, region is technically a boat. I think
It
that's
is.
what
It's a
we learned
boat.
here in the podcast when Billy was here.
Yeah,
Um,
don't
it,
ever
it,
call it
it,
an airplane.
yeah, it's covered by the aviation media space because it's flying. It's a flying thing, but it's technically a boat because it goes so close to the water as a ground effect vehicle. So that's maybe a discussion for another day. I mean,
Yeah,
I would post a link to that episode so that everyone can get familiar with that concept as well. But yeah, sorry, I interrupted you. So
yeah, no
you were
problem. So
designing this plane that has this kind of drop of bullet shape, and that's because it takes advantage of the laminar flow
yes,
phenomenon, right? So
yeah.
what's the laminar flow and what does it do to an airplane?
Yeah. Laminar flow, most simply put, is the orderly flow of a fluid over a body. And what you want to do is contrast it to what we're more familiar with when we fly, which is turbulent flow, the disorderly flow of a fluid over a body. And the difference between those two types of flow is drag. Laminar flow is 5 times less draggy or 5 times more efficient in drag than turbulent flow because it reduces the viscous drag. Viscous drag is the friction that the air feels against the body of the vehicle, whether it's your car or an airplane or anything else. And natural laminar flow, which is what we always talk about, is based on two things: the geometry that you create on your airplane and the state of the fluid that you're flying through. So its viscosity, its density, et cetera. So, and that number there is something we call the Reynolds number. So the geometry and the fluid that you're moving through and the speed and the altitude amount to what's called a Reynolds number. And you want to keep that nice and low so you can accomplish your natural laminar flow goals. There's also hybrid. You'll hear about hybrid laminar flow. That's when there's a system on the aircraft that is trying to induce laminar flow, like a suction system to keep the air closer to the surface, or a blower system to try to control it over the surfaces. Ours is natural. We like it that way because those extra systems tend to be complex and hard to maintain. So yeah, so the Celera 500 has two areas of really important laminar flow, and we'll talk about that on the Phantom too. The fuselage, but and that's what people are always drawn to because of the unique shape. But really, more critically, is the laminar flow on the wing. And on the Celera 500 here, you got about 7 foot, 7 feet of 2 meters for your European folks
Hmm.
of laminar flow across the front of the aircraft. And then on the wings, you have 35% coverage of laminar flow. On the Phantom today, I won't jump too far ahead, but we have about the same ratio of laminar flow across our fuselage. It's more like 12, 15, maybe 17 feet, but our wing is 90% covered by laminar flow. So it's a really, really big deal. But yeah, the Celera went through a short flight test program. And the reason why it was short, people always ask, what happened? And it was just so successful. The aircraft was meant to go up and measure laminar flow. And how it did that was we measured the thrust, we measured the fuel burn, and then we used infrared, a type of infrared camera to look on the wing and on the fuselage to see where laminar flow transitioned to turbulent flow. Turbulent flow and laminar flow have different thermal properties, and you can pick that up in temperature sensitive paint or with certain high precision thermal cameras.
And
Yeah.
that was in around
Yeah.
2015, 2018, more or less,
Yeah,
right?
no, that was more like 18 to
Okay.
18 to 20.
And you
And
had
so
one aircraft, one demonstrator.
yeah, one demonstrator. It was
Uh-huh.
all of it was made by Otto Aviation themselves, except for the tires, brakes, propeller, avionics, and engines. So the
Okay.
team was very scrappy and very self-contained at that time. And
Hmm.
we're benefiting from that today, plus adding some, legacy folks like me to give us the aerospace certification and production discipline.
Hmm. And then what happened next? Because then, of
Well, I
course,
mean, like to all of
yeah,
us, it was kind of COVID after that.
of course.
Yeah. So it went quiet during COVID. And as COVID starts to break in the 2022 time period, that's when we started to, look at things. And we were probably looking with some of our folks earlier, but New Vista Capital, Paul Tao, my boss and our CEO, he was a part of that group. His wife was one of the founders of it. And we would look at deals all day long of aircraft technology, A&D technology. And we saw Otto and thought, well, we'll go take a look. And Paul went out and he made a proposal to them where he said, look, laminar flow is amazing. How about we try to bring it into a juicier part of the market as our initial product, never forgetting the great roots that the Celera created for us, but more importantly, using the learning it created for us. And let's transform this into a super mid a business jet, the sweet spot of the business jet market.
Because what?
And
Sorry, what
let's
what what was the original intention to make it make a plane for general aviation for
This would
private
have been
pilot?
the Celera 500 would have been a GA, application that
Uh-huh.
is subsonic in its speed. The Phantom today is transonic, so that's a big deal for laminar flow as well. And
And it's a jet as well. The first one was a
yeah,
turboprop.
no, not a turboprop. There's a turbo diesel engine
Okay.
that drives a drive shaft and then drives the propeller. And then
Okay.
the new aircraft is a turbofan, twin turbofans. Yes,
Okay. Hmm.
twin jets.
Yeah. Sorry. So I interrupted you when you were explaining. You then decided to pivot onto the
Yeah. So
super
Paul,
mid-sized
yeah,
executive jet market. Yeah.
yeah. So Paul went out and he said, "So let's get a little bit of a better product and product space to focus on, and let's build a team that can go the distance through prototyping, certification, development, production." Because the team there at Otto was fantastic, very scrappy. I told you the stories about how they built the aircraft themselves. But aerospace is hard and requires a certain amount of different disciplines to be involved. And the folks at Otto accepted Paul's idea, made him the CEO, and then he went to find somebody who could design, build, test, certified, produce the aircraft. That's me. And he asked me to join in the fall of 2022. So I joined in October 1 of 22. Paul was there from probably the spring or summer. And we probably looked at Otto a little bit before that too with some of our other advisors. And then we kicked it off. So I started to build the team, started to bring suppliers closer to us. Paul started developing the mission and the vision and the commercial business part of it. Paul's also an engineer, so we were working the engineer and technical stuff together too, which is great. And Paul's a great entrepreneur as well. His background, he was one of the co-founders of Ariba Software, one of the largest supply chain softwares, B2B supply chain softwares in the world.
Uh-huh.
He was also the co-founder or founder of ExoJet, the first kind of, Uber of the skies with business jets. So we started to build the team and design the aircraft. We went right into our systems requirements review and then started to conceptually design the aircraft. And it was going to be right there in the super mid space. And what we found because of laminar flow is that with reducing the drag by about 30%, which is what our calculations were telling us, we could reduce the size of the aircraft by 50, almost 60%. And so a 40,000 pound super mid today, like a Citation 10 or a Challenger 3500, is our competition, but we weigh 19,000 pounds because when you reduce the drag, and this is what we call the virtuous cycle of aircraft design, when you reduce the drag, you reduce the amount of fuel you need. When you reduce the drag, you reduce the amount of thrust you need. And when you have less fuel to carry around and less engine to carry around, the structures can shrink. And then that whole phenomenon starts to take over again until it converges to what we're going to do as a 19,000 pound aircraft. Now, 19,000 pounds is not random, or because 19,000 pounds is the maximum takeoff gross weight for a Part 23 aircraft. Our competition also lives in Part 25. We're going to be in Part 23 and provide all of the same services that a super mid does. Coast
Okay.
to coast in North America, 0.78, zero point 0.8 cruise Mach number, an 800 cubic foot cabin with a gorgeous customer experience inside, and all of the things that someone would look for in a super mid, but in a smaller, more comfortable package, actually.
One of the features of the aircraft that I'm sure you get lots of questions about is the absence of windows,
Yes.
right?
Yeah.
So, how are you dealing with that? I mean, first of all, what are the reasons for that? Which
Yep.
I kind of guess from what you've been telling us. But yeah, can you tell
Yeah.
us a bit more about this? And also, how are you dealing with that? Because it's apparently like a not so important point, maybe, but from the point of view of the psychology of
Right.
potential customers, I guess it's pretty important, right?
It is. Yeah, I'd love to talk to you about that. So I'll tell you how it started, then we'll get into the customer experience part because you're right, that's the most important piece. So it started with the notion that we don't like drag. We are a low drag company. In fact, our mission is to reduce the energy required for flight. That's what we do. So laminar flow helps you get a long way doing that. But if you also constantly have a mindset that's thinking about drag, you could attack what's called excrescence drag as well. And excrescence drag is, bumps and cutouts and antennas and doors and things like that on your aircraft. And we thought, well, let's reduce that. And we took the windows out in the cabin. And then we said, well, what are we going to do inside? Because that's part of the customer experience. And we came up with this concept called supernatural vision. So the inside of the aircraft will have digital windows. There'll be OLED screens, and you can watch live outside of the aircraft through camera feeds. You could do entertainment. You could do business applications like we're doing today. You could use it as a lighting or an ambiance type of setup. Very powerful combination of different types of customer experience. And you're right, the psychology has been studied. We're studying it. In fact, we hired a person from Apple, Craig Lewiston, who's leading up that group for us. And Craig worked in the human machine interfaces of some Apple products like the watch and other things. So he's very keen on keeping the ears and the eyes attuned because
Okay.
when your inner ear and your eye get out of sync, you don't feel very well usually. And he's working really hard on that to keep that together. And it's very doable, and we're starting to get very positive feedback from customers or potential customers that come out and see it, investors. It's a very, very nice experience.
And I guess you've been designing as well a cabin interior and all the decor and everything
Yes.
that goes with it. For how many people? How many
Nine
passengers?
people. Yeah. Super mids are nine
N-
people. Sometimes
Nine,
they're 10,
nine
but
passengers. I mean, not counting pilot and crew.
correct. Yeah.
Okay. And what's the range of this aircraft?
So coast to coast in North America. So you're looking at 3,000 to 3,200 nautical miles is our target.
Uh-huh.
And we're looking pretty good there. That would be with five souls on board, MBAA reserves, and all that. And then, of course, with the payload range curves, as you may know, if you don't have anyone on board and you're doing a repositioning flight, you can get, higher ranges than that. If you put more people on board, you get lower ranges. But the super mids, in order to really be a super mid, you want to be able to go coast to coast in North America. You don't have to get across the ocean. So think about the Praetor 500, the Citation 10, the Challenger 3500, those types of aircraft and their capabilities.
Could you do transatlantic with a right payload?
Um, it's kind of close. You wouldn't make it back, but you might be able to go there. But we're not advertising that
Okay.
or talking about that as part of the mission.
Well, I
It's
guess.
something we are thinking about it though in an upgrade, a block upgrade.
Uh-huh.
You'll sometimes hear us talk about that next aircraft, and we would like the next aircraft to be not a full redo, but enough to give it legs to get across the pond because
I
that's
guess
a
it
people
could
want.
get there eventually with one stop, I guess, in
Oh
Iceland
yeah,
or a
you could
place like
easily
that.
do
Yeah.
that. Yeah, yeah,
Yeah.
yeah. You could go to
Um,
ice.
one thing that also caught my attention is that you are planning to fly way higher
Yes,
than conventional aircraft.
yes.
Tell us more about that.
Sure. Well, again, that goes back to the Reynolds number that we talked about before. When you're up at that altitude, you have much less viscous drag because of the density of the air, and it allows you to keep your Reynolds numbers down. And it creates a certain tolerance for those, pragmatic things that you have to think about on an aircraft all the time: abrasion, bugs, steps and gaps. The higher you're able to fly or the lower Reynolds number you're able to fly helps you preserve the laminar flow that you're looking to keep during the cruise mission. And it helps you achieve lots of other things too, like you're up there without anyone else. There's not a lot of traffic up there, so you can get clearance to there. You're above the weather, the jet stream. You also are in an atmosphere that's very dry, and contrails are minimized at that altitude. So when we get to talking about our sustainability capabilities, we have to talk about CO2 reduction and aircraft induced cloud induction, which is very, significant in terms of contribution from aviation to global warming. But yes, we fly high. And this is a good time to tell your audience how that works, because people know that, well, when you fly high, it gets mushy up there. And how do you get up there so fast? Doesn't it take so much time? Well, here's kind of how it wraps around the wing. We call our wing a big dumb wing. And that's because our wing loading is low. We have a big wing. And people say, well, that can't be good. It's going to be draggy. Well, it's not, because it's in laminar flow. And so all of the lift characteristics of a big wing are with us, but all the drag characteristics of a big wing are not. So our L over D is very high. So when you're down low near the runway, you have a very good balanced field performance. We can get into more airports than our competition at 3,500 feet. It's really short because of that big wing. That big wing also pulls you up to that altitude very quickly. And so you don't have to spend a lot of time going to that higher altitude or step climbing. And then the third thing it does when you're up there, and normal airplanes get very mushy, Gulfstreams and that Cessna's Citation 10 can go up there too, but they get mushy, and pilots don't like to fly when they don't have a lot of, that good feel. And ours does, because again, it's a big wing. But that big wing disappears in drag due to its laminar flow performance.
Okay, yeah, I read you claim that the aircraft is going to provide a 50% drag reduction overall and a 30% increase in lift, right?
So 30% reduction in drag and a 60% increase in efficiency. So
Okay.
yeah.
I was at the presentation you guys had at the Paris Air Show, where it was very focused on sustainability. And you also have a pretty strong claim there, saying that your aircraft would produce about 36 grams of CO2 per seat mile, which
Yes.
is pretty impressive. I think one of the airlines that has the strongest claim to having a low carbon footprint is Wizz Air. That it's around 52 grams, I think. So, and you even claim it's on the same range as as an electric vehicle, like a
Uh-huh.
car. Yeah.
Yes. You can do two things. I'll take you through. So
And
if
using
you,
SAF as well, because
yes,
let's introduce this other topic. Your aircraft is going to be using fuel, so it's a combustion engine. It's not
thermomechanical
nothing
engine.
electric or hybrid. It's fuel, but it's going to be very heavily oriented towards SAF use. Yeah.
Yes. Yeah, we would like, so the first couple things is our engine, our fuel system are both certified for 100% SAF, sustainable aviation fuel. But the thing everyone needs to remember is that, why don't we use SAF today? Because a lot of engines are like that. SAF is too expensive. And so you pay that so-called green premium that we often hear people like Bill Gates talk about. But
Mhm.
if you take our aircraft and remember the story of what we did with laminar flow, we reduced the weight of the aircraft by half.
Mhm.
When you do that, all of your costs, your acquisition costs, your manufacturing costs, and your direct operating costs go down. And so you can provide a very nice savings to your customer if they used Jet A. But if they choose to use SAF, sustainable aviation fuel, yes, they pay more for that, but it doesn't take away the net discount that you would receive.
Mm-hmm.
So with Jet A and a reduction of 60% in CO2, you can be pretty happy about that because we're burning 100 gallons an hour and they burn 300 gallons an hour. That's roughly the math. But on SAF, you can get your CO2 emissions down by 92%, almost down to zero. And yes, you spend a little more money, but you still save dramatically against the competition, which would have to burn SAF and charge you for it in addition to what you already pay.
The 90%, I'm assuming if you're using synthetic SAF, right?
Yeah, that's with the SAF. Yeah. Hmm.
Yeah.
And that's carbon dioxide measure. When you look at the EV comparison, you have to just, I'm always very careful about this because I believe engineers, should be. You can play games there all you want, but if you're in a place that already burns hydrocarbons as their primary means to generate electricity, then you have a certain measure of carbon dioxide per seat mile in an electric vehicle, a car.
Yeah.
If you live in France, where they generate the preponderance of their electricity through nuclear, then you might have another number because you're not, entering
Yep.
into a CO2 loop.
Mm-hmm.
Uh, so that's one thing to keep in mind. But the beauty of ours is that you get that kind of efficiency and you're going 500 miles an hour instead of
True.
50.
Yeah.
And that's pretty impressive. And it just shows the power of laminar flow, that reduction in drag, reducing your typical fuel burns of 300 gallons an hour to 100 gallons an hour. It's just incredible. 300 gallons an hour is what you and I use taking our families around in a car all
Okay.
year. That's,
Uh-huh.
I mean, that's a big, that's a big hour for these vehicles. So we're very proud to have changed that and given people the option to contribute to the environment in a positive way.
Mm-hmm. And to this you add non-CO2 benefits of
Yes. So
reducing these non-CO2 emissions as well.
exactly. You have one when you fly at 51,000 feet, the air is too dry there to create contrails, and contrails are it's water. But when they're released in the atmosphere, when water is released in the atmosphere like that up high, it creates aircraft-induced clouds. Clouds tend to be warming effects on the environment. So, and aviation, although not a huge global warming contributor, we all have to do our part though. A big portion of it is from the contrails, and so we have eliminated that as well.
Mm-hmm. So basically, if we look at everything together, CO2, non-CO2, can you put a number on this compared to a similar aircraft, an aircraft of a similar size, in terms of, let's say, the sustainability efficiency improvement that you provide?
Well, yeah, there's actually a new part coming out soon. It's called Part 38, I think it is. I'll double check that for you.
Mm-hmm.
Uh, but it's basically a new regulation in the FAA that requires a certain amount of efficiency performance.
Mm-hmm.
Well, all of the current aircraft sit right on the exact line defined by this new part. We're like 40% below it.
Okay.
So I would say that's the best measure of it. If you take all the airplanes out there that are going to be subject to that new rule and plot them on the line, we're below that by about 40%. So, I
Mm-hmm.
mean, one thing to be careful about with SAF, when you talk about like NOx and other things like that, SAF it has the same specification as Jet A, and it's still it's a liquid hydrocarbon. It's just that you create it through agricultural waste products. And
Mm-hmm.
because the cyclical effect of taking that carbon dioxide out of the system all the time gives you that benefit, but you're still burning a liquid hydrocarbon.
Yeah. And let me ask you this question. If obviously we heard all the benefits, but if this is so good in all respects, why it hasn't happened
Yeah.
earlier? Because you mentioned like this laminar flow phenomenon. It's been known for quite
Oh
some
yes.
time.
Oh yes.
So why no one has done it before? Why we don't have many more aircraft based on this principle?
Yeah. Well, it's, we could talk about this whole thing for a long time, and I used to have to do it more when I was in innovation at Bell. One thing is the innovator's dilemma. When you're an aircraft company that is successful, and maybe your success started in the 70s or the 80s, and in the 70s and the 80s, you were building aluminum aircraft with rivets and traditional means without the digital tools that we have today. And you're selling and nobody's asking, what's the gas mileage on my superjet here? Because people don't ask what the gas mileage is on a Ferrari or a business jet. They don't have to. Um, so you get into this pathway where now all of a sudden you've hired everybody who knows how to work in aluminum. You've made an entire factory that works in aluminum, and you have a system that supports that kind of aircraft. Well, to step off of that, if you're already successful, is a very difficult conversation for some companies to have. We don't have to do that because we're a startup. So that's one reason. The other reason is composites, and that is graphite epoxy composites, are now really coming of age. 787, stealth fighter. And when you look at that technology, it's absolutely necessary for laminar flow because you can create very low waviness on the surface of the aircraft, skin waviness. You can create very small deterministic steps and gaps, meaning you decide what they're going to be and you make the part to have that tolerance. And that's important for laminar flow too. And it's just an amazing effect. One of the biggest analogies we make, and I think this will be good for your listeners, is if you've ever been up near a stealth fighter, the F-35, you'll notice it's very smooth and it has very minimal steps and gaps. Why do they do that? To evade radar. We do it to evade drag. And so that's kind of the easiest way to think of it. And that technology is now available today. The other thing is that laminar flow is difficult to predict. And if you can't predict it in a meaningful, consistent way, then you can't invest in doing it. And now we can predict it with proprietary codes that Otto has, and we run on the supercomputers that everybody else runs on, but we have a special code that helps us do it.
All right. So basically, let's say you are successful developing this aircraft. What is the road to market? What are the next steps? I guess first certification, then market it to prospective
Yes.
customers in the executive jet market. What time horizon are we talking about here?
Yeah, so we will have our first prototype of the Phantom jet in flying in 2027, mid to the latter, later 2027. And then we'll build four more prototypes. The first one will be a production representative. The last three will be certification qualified for conformance. And then we'll begin production probably in late 2029, and we'll build maybe 6 to 8 aircraft prior to certification just to be ready. And then we'll get certified in late 2030 and begin our production run from there.
You're planning to produce them in Jacksonville, Florida, right? I think
Yes, yeah,
it was announced during the Paris Air Show, supported by the state of Florida.
yes. We received $500+ million in grants and incentives from the great state of Florida and the city of Jacksonville and the county there, and the airport. They were big supporters too. And we're going to build a brand new factory there on a green field and produce the aircraft there. But we have a hangar there too that's existing already. It was an F-18 maintenance hangar, and we're going to build the first four prototypes there. So we're
Mhm.
going to all start moving out there in 2026. But yeah, it's going to be great.
Because right now you are based in Texas, is that right?
Yeah, yeah. There's my you can see my
Yeah, in the Dallas area, right?
Fort Worth. Yeah,
Fort
we're
Worth.
at the
Yeah.
Meacham International Airport right now, and that's
Uh-huh.
where we have about a third of our workforce. We build our mock-ups there, our lab for supernatural vision, our flight deck labs. We have a machine shop and build different things that help us understand how the aircraft's going to be.
So that's
Yeah.
a pretty substantial amount that you mentioned, 500 million.
Yeah.
Are you, I mean, how are you guys funded so far? Are you,
Yeah.
have you received venture capital funds?
Yes,
Are
we're
you in the
venture.
market? Are you in the market for more investment as well? Because I guess 500 is a lot, but you would still need
Oh, yes.
a few
Yeah.
more million
Yes.
to bring this to fruition,
Yeah.
right?
Yes. A few more hundreds of million.
Yeah.
The we are venture funded to date, and we just closed our Series A funding in or the earlier part of this year. And yes, we are looking for more funds in our Series B, which is now open. The Series B will be a larger venture, and it will carry us through that flight test vehicle one that I told you about, plus a bit afterwards. And then once the aircraft's flying and everyone sees what it does, it'll really just knock all the dominoes down. But yeah, we've also received some funding from the FAA and NASA. We won the largest Fast Tech grant, which is a grant program in support of sustainable aircraft flight. Jet Zero and us, we both won the largest grant there, which was great. That was last year.
And what sort of amounts are we talking about when it comes to the
The
Series
FAA
A?
grant, the FAA grant was 7 million. Our Series A was roughly around 100 million, a little bit less. And then we need you need something like $1 billion to do an airplane project like this, but you
Mm-hmm.
don't raise all of that money in aerospace. You raise money from your sources, whether it's your parent company or venture capital, and then you expect, as we do, our partners to contribute to the program for the privilege of being on board with us.
Mm-hmm. And what's the total addressable market that you have in mind? How many aircraft you plan to produce once this factory in Florida is at full production?
Yeah. We will, when we're at full rate in about 2035, 2036, we will produce 220 aircraft a year. So that's one a day. And we think there's probably 1,600 of them for us to sell. And that'll be, all in parallel to whatever new models we come up with. The TAM in super mids, I think, is 24 billion just in the super mid area. But we have the capability to go downstream a little bit because we're so fuel efficient. We're more for fuel efficient than medium and light jets, actually. So we might be able to figure out how to get those customers in too. And then if you go on the higher side and try to build a larger aircraft, that expands again. And we're looking forward to doing that as we succeed on this first project.
Mm-hmm. And what about the customer service network? Because I guess in
Yeah.
this type of market, this is very important to have a post-sale
Yes.
service so that private jet owners can be reassured that they're gonna be getting the right service at any time, any place,
So
wherever
we're
they
we're gonna
are.
have
Right?
a first. We're gonna have a first in history customer service plan called the GUP. It's a guaranteed uptime. So that means when your aircraft's down, we're not only going to come and fix it, we're going to come with another aircraft and take you where you have to go.
Oh wow.
So you're not gonna. And again, it's the economics of this of
Mm-hmm.
laminar flow that allow us to do that and provide that service still at great savings to the customer. And that's a wonderful service if you think about it. So the idea is to have a small separate fleet, maybe one out of every 8 or 10 aircraft that we build. We separate them off. They provide the GUP service, the guaranteed uptime. And when they're not doing that, they can charter and do other things, do demonstrator flights for us, marketing flights for us. So that's going to be really important. Now, we need a good partner there because our startup philosophy is not to, devour the universe like a lot of startups do. We are a final assembly integration and test OEM. So we partner with folks to make systems for us for the aircraft itself. And we might well partner with folks to do our services too. And that could range from a fleet operator that is also a customer or to the maintenance folks that are out there already, a West Star or a Duncan or something like that.
Mm-hmm. Uh,
Yeah.
do you have a price point in mind for this aircraft?
Yeah, we're not really talking about price right yet. I think the best way for everybody to think about it is the cost function that we talked about. You can
Mm-hmm.
when you plot costs on an airplane, it's linear with max takeoff gross weight. So if we are 50% less max takeoff gross weight than our customer or our competition, that's our cost opportunity. Now,
Mm-hmm.
we have to spend a little more for certain things because we're trying to make a structure in a certain way and have other systems on board. But that's roughly the calculus that people should keep in their minds. But it's too early, really, for us to talk about price.
Mm-hmm. You mentioned it's going to be pretty much all composites
Yeah.
when it comes to the structure. We haven't talked much about the engine. I guess you,
Yeah.
you, you have an engine partner, right? That's going to provide.
Yes,
You have
Williams.
selected. You have selected
Yep.
the specific engine that you're going to be using for this aircraft.
Yes. It's the Williams FJ44-4,
Okay.
the version that has quiet power mode on it. So we do not need a APU. This wonderful engine will run kind of idle while you're on the ground and not count hours against your engine time and provide power for the air conditioning and other systems that are necessary for preparations on the ground and the flight.
Mm-hmm.
It's a great engine, SAF ready to go to 51,000 feet. So, and it's got 13 million flight hours on it already as an engine type. So it's a really reliable. And that's another big story about us. We try the aerostructures are always bespoke, and our aerostructures are very particular because we want to accomplish laminar flow. But
Mm-hmm.
otherwise, we're looking for commercial off-the-shelf equipment, commercial off-the-shelf engine, avionics, fuel systems, landing gear as close as it can be, all of that, because we want our certification risk to stay low. And you can do that by using systems that have already been in circulation for a long time. We don't have, for example, this is not fly-by-wire. This is fully reversible mechanical controls. In fact, fly-by-wire would be too heavy, too expensive, and create certification risk in this category. Although it's like that, it's in this category in our competition, but we don't need it at the new weight. So all
Mm-hmm.
those things add up to a very clear certification path. Certification is never easy. It's never to be taken lightly because it focuses on safety. But we're trying to make sure that we are not very new and novel, except for laminar flow. And laminar flow, remember, is a performance measure. If we don't achieve laminar flow, that's our problem. It's not related to safety, so it's not really a certification issue. But I
Mm-hmm.
mean, we prove that it's there and watch the aircraft as it transitions in and out of it, but it's not a big deal from a safety standpoint.
Just to wrap it up, what sort of interest are you getting from the market? What sort of feedback?
We're getting great interest. I mean, we've talked to several of the bigger fleet operators, and one, they give us, a lot of props for the beautiful interior and the supernatural vision. But the biggest thing, you can imagine how much money we would save for the bigger fleet operators just in fuel burn alone. It's an enormous amount of money. So they love us for that. And they think we have a great team, which we do. We're still, early days in a startup. That's always makes people nervous. But I think we're going to have a very, big year in terms of some customers potentially coming up and wanting to partner with us.
So, if people wish to learn more about this project, what sort of resources,
Yeah.
websites, social media
Yeah.
channels can you? Yeah.
Go up on our website, which is www.ottoaviation.com. There's a lot of great information up there. And we also provide some pictures and media resources. We talk a lot about what laminar flow is and what we're planning to do. So I think that's your best place. Keep track of us on LinkedIn. Follow us on LinkedIn. That's another great spot. We love to not only talk about our aircraft, but we talk about our people there too. And I think that helps with partnerships in the supply chain. It helps with recruiting. It helps with to feel like our community is a part of this, which they are. We're going to do tons of stuff in Jacksonville, but we're already doing a lot with some of the local schools and things in Texas as well. So that's another great place to follow us.
Excellent. So it's just left for me to say thank you so much, Scott, for being here today on the podcast and sharing these amazing details about this project, which I think it's one of the most transformative right now out there in aviation because of all these many different innovative features that we've been going through. So
thank you, Miguel.
Thank you so
Thank you
much.
so much.
If you like this podcast, you can support us by giving it a great rating on Apple, Spotify, or whichever platform you get it from. And remember, you can, of course, subscribe to it. And you can also get regular updates through the Allplane website. That's ALLPLANE.tv. We have a newsletter where we cover the aviation industry every week with a special focus on innovation and sustainability. So give it a go. Thank you and goodbye.